Yeah, now let's go on to the second part of the tutorial set. Okay, so this time around we ended at problem 5. So we are proceeding with problem 6 to the last problem, problem 10. Here we are still on the pressure measurement. Okay, now we are to determine the maximum pressure gauge. Okay, or let's say the maximum gauge pressure in the oil tank shown in the figure. And then also we are to tell the location where this pressure will occur. And then finally, we are to look for the hydrostatic force acting on the top part or the top CD here of the last chamber. We have chamber 1, chamber 2, chamber 3, and chamber 4. Okay, the last chamber on the right-hand side of the tank. We are to assume a temperature of 10 degrees Celsius. All right, now pay a closer look at this diagram. You did technical drawing or engineering drawing. Now, over here, the tank, this is the front view, or let's say the side view. Okay, at least that will give you the detailed, let's say, the front characteristics of the tank. Okay, now you see the view they've indicated here, view EE. You see the arrows are directed downwards on top of what the front view that we are looking at. So meaning this time around, if you look at view EE, you are going to see the top view, which is more or less like the plan view. That is what is even on top here. So this part here, this line here is that. Now this line here is this line. And then the broken lines, the other one is here, and then that. Meaning that this top part, you can see is a thick black line, right? Meaning it's sealed. The only open portion is this part here. So if someone should jump into this tank, he or she would, let's say, swim through, get to this point. It's still water, here is air, probably try to climb and jump into this liquid now. This liquid we are saying is having what? A specific gravity. Here is SG or S, okay? Gravity of 3, meaning that if you want to know the specific weight, you just multiply this value by what? Water, okay? The specific gravity of water to get the specific weight, the specific weight of water to get the specific weight of the liquid here. And then once you get inside, you can also swim to this part here, the air. Okay, so remember that the pressure that will happen, or let's say that will occur on this surface, will be equally distributed on the surface here. It will be the same pressure acting on this part of the wall and that part of the wall and that part of the wall here. So we only need to get the pressure here. We good? Okay, that's fine. So now let's move on, okay? All right, so by moving on, we are to find the maximum gauge pressure in the oil tank. All right. It's the same thing as the YouTube manometer, okay, or the manometric analysis, okay? Good. So let's see how best we can do that. Now let's take the oil tank again. Now we have this part labeled 0.1. You remember this equation, right? Okay, good. Now we have this part labeled what? Let's say 1. Now, what we need to do is that we are saying that if we are looking at, let's say, the fluids here, remember the pressure will be due to, is directly proportional to the weight of the fluid, right? If the weight is higher, meaning the pressure too will be higher. So at the bottom, of course, the maximum pressure will occur at the bottom of the tank. But at which part of the bottom? Is it at the bottom of the liquid, sorry, the water, or the bottom of the liquid with specific gravity 3? You see, now obviously I'm saying the maximum pressure will be at the bottom of the tank, but under which fluid? Water or liquid with specific gravity of 3? The correct answer is under the one liquid with specific gravity, this, since it is heavier. Okay, good. Now, let's see where we are talking about. Under this liquid with specific gravity, this is the part we are talking about here. So any part here along this part can be where, so anyone here will be feeling the weight of the fluid at this point. Okay, good. So let's see. Now, using the general formulation shown, this part here, and moving from point 1 to the point P max we have. So we are moving from here till we get to any part here. So which class am I in now? Let's say I'm in, whose name can I remember? Okay, don't worry. I'll get the names. Now, he or she jumps from, so we are using the walking through method. So from point 1, you dive into till you get down here. So move from here to here. But remember, from this part here, this level here is the same thing as what? This is the same fluid, right? So if I move down here and I move up, this part will cancel out. So I can only focus on, let's say, this part here, right? This height. And that will do the job. No, so now from here, I will move up. Now, when I move up between this part, when I go here and I get down, is the same fluid, which is air. So upward movement will cancel what? The downward movement. So I will only need this part here. So from here to here, then I'll get to this part, then I'll forget the top one, and I'll get to this point because I want the maximum pressure. I'm not going to end here because I'm not going here. I'm aiming at what? Ending at P bottom. So I'll go to P bottom. I believe by now you guys have obtained the answer already. Now let's see how best we can solve that or apply that into practice.
All right. So let's see. We are saying that first of all, I've ruled this line here to get rid of what? The negative and then the positive part. The next line I'll rule is up here for the air section. And then the last one, that's it for now. Okay, good. So first of all, P1, we are moving to 0.1. So P1 plus what? The pressure as a result of what? The water column here, the water height here. So we have what? P1 plus gamma of water. What is the distance from here to this part? We have from here to here is 1. From here to here is another 1, so 2. And from here to here is 2, so 4. Right? So all the way we are moving from this point to the point here. So times 4, gamma of water times 4. Then remember, we will move down here, it will cancel here. So we just come and start from here. So upward movement, negative, right? Minus. So first of all, okay, the arrow indicating the direction that we've chosen. So secondly, we'll go to the air column, air gamma times 2, right? Gamma air times 2. Okay, good. Now, if we do that, we will have what? This is the arrow I'm talking about from here to here. And remember, this part and that part will go off. Okay? So we are now here moving down to the last point. So plus gamma of the fluid with specific gravity 3. You know, so good. So times what? 3, because from here to here is 2, from here to here is 1. So 3. So this will now be that. And once we are at the point here, we equate to what? The pressure there. That's P max. Okay? All right. So with this, what we need to know is that this gives the value for what? The maximum pressure at the bottom. Okay? All right. So now the data given, we have the data to be what? Remember, P, the surface 1 is what? Exposed to what? Atmosphere, right? So P1 is what? 0 Pascal in terms of gauge, since it's open to atmosphere. Gamma of water is 9810, blah, blah, blah. So if we are talking about, let's say, specific gravity to be that means the gamma of that liquid will be just 3 times what? You are asking, you are wondering it. Sorry. Let's see how we had that. Please pay attention. Please pay attention. Why am I saying gamma S3 equals 3 times that? Because S, okay, is equal to what? Gamma of the fluid, which is now that all over what? Gamma of water. Okay, so this implies that if I want gamma of the fluid, which is gamma of the fluid is S equals 3, this will now be equal to what? So gamma of the fluid is just equal to what? The 3, which is the specific gravity, multiplied by what? The gamma of the water. Okay, good. That's why we have it nicely written here. Okay, and that will give us 29,430 Newton per cubic meters. Okay, so what then is the P max? So we know all these things now. So we simply rearrange and put in the values. P1 is 0. This, we are to neglect changes in what? The air, right? So neglecting pressure changes in air. If it's silent, you can still use them, but then it will not have any impact. It's just some small value compared to the pressures of the other liquids. Okay, good. So at the end of the day, we have this, and when we simplify, we have 127.53 kilo Newton per what? Square meters, which is actually kilo Pascal. Okay, good. So now we are saying that this is answering what? Part A of the question. And the maximum pressure is going to occur at where? The maximum pressure will occur under what? The liquid with what? Specific gravity S equals what? 3, this part. Okay. It can be here, it can be here, not necessarily at this point. Okay. It can be any point under that. Thank you. So now we are left with part C of the problem. So if we look at the diagram again, now this is what we are dealing with. The last part is saying that we have to now find the hydrostatic force FCD acting on what? The top CD here, right? Now remember, we can find the force if we know the pressure, because I know that pressure is equal to what? Force over area. So this means that my force is simply P times A. And remember, because we are looking for what? CD, we are looking at what? P acting on CD, it will be the same thing as what? The pressure, sorry. Since we are looking for what? FCD, we are looking for what? PCD, and that's the same pressure on the surface. It will act on the same. So if you're able to estimate the pressure here, we are done for the pressure acting on CD, and then we use this equation. We know the area, because what type of geometry are we talking about here? We have a square geometry, because the length is 1 and then the breadth is 1. So 1 meter, 1 meter. So the area is simply what? 1 times 1, right? Good. So we are saying that for the hydrostatic force, FCD, now acting on this of the last chamber on the right-hand side of the tank, we again apply the general manometric what? Equation, okay? The general manometric equation moving from point 1 to 2, since P2 will be equally acting on all surfaces within the last chamber. Thus, here the P2 is actually the PCD, okay? The pressure acting, that's the pressure of the air, okay? So first of all, we say P1, already we've established that we are moving from 1 to that place. And remember, we go to what? This point, right? Now, what do we need to do now? We have to just subtract this part out of it, right? And moving up now is like what? Just 1 minus. Remember how we had this? We came down here, move up 2, minus, move down 3, and then we are here, right? So that is what this arrow here account for the last term now. Gamma times 1, or that same fluid, right? So now, what do we need to do? This value is no more equal to the maximum pressure, but it's equal to what? P2, okay? And where is that 2 that we are talking about? This is the 2 we are talking about here. Okay, P2. Are we good? All right, so if we simplify this, we end up having P2 to be equal to that 0 in the sense that it's exposed, blah, blah, blah. And then we neglect changes, pressure changes in air. And then we end up having P2 to be this expression. And this, remember, this is just the maximum pressure we obtain, right? So this value will decrease the pressure by that. So we end up having 98.1 kilowatt pascal or kilonewton per watt meter square, right? But knowing that pressure is equal to what? P2 is actually FCD over what? PCD, because P2 is the same pressure acting on all the surfaces here, okay? So if we know that and we make FCD the subject, that's what I mean by that. It implies that FCD is equal to a P2 times ACD. And ACD is the area we need to find now, right? So that area is actually the shaded area now. The shaded area here. Okay? So which is what? If we look on top, that's what we see. So the force acting on this is what we are looking for. So we end up having ACD to be what? 1 times 1, right? Which gives us 1 meter square. And then this will give us a force of what? This pressure times the area, 98 kilonewtons, okay? All right. So that is a good one, right? Please, all your questions, replay the videos over and over again and everything will be fine, okay? Good. So now we are on the 7th question, which is determine the force acting on one side of a concrete form, 2.44 meters high and then 1.22 meters wide. That's 8 feet by 4 feet, okay? That is used for pouring a basement wall. The specific weight of the concrete is what? 23.6 kilonewton per watt cubic meters, okay? Now, this is what we are doing. So for the solution here, like I discussed with you the last time, the concrete form is normally the wooden structures they create. That's the masons, those builders, before they pour the concrete to solidify to hold our buildings in terms of beams and then the rest, okay? So now we are looking at one form of it, okay? Now, don't worry, this diagram will be clearer. We are to determine that. So if this is one form of the concrete wall form, okay? One wall of it, okay? One of the walls. So I'll extract that right now for you to see. So with the 2, we have them this way, and in between this, we fill the concrete, okay? So filling this with concrete, this is what I mean by that. So it is filled with concrete. All right. Now, we are to determine, they give us a dimension, right? So for the height is 2.44, and then the width is what? 1.22 meters. So here, we need to now focus on one part of the wall, which is what? One part of the form, concrete form. That's one wall. We can take the left one or the right one, but for now, I'm using the right one because I've highlighted on it, okay? So if I decide to pick that one, this is the way I'm picking it out of it. Now, we need to locate the centroid. We know this symbol to be the centroid, right? That's more or less like for a rectangle here, it's more or less like the middle point, okay? All right. Now, we need to know the center of pressure where the force will be exerted, which by definition is located a few distance below what? The centroid of what? The figure. Now, this is it. So at this point, we are saying the resultant force will act on this point, which is what? The center of what? Pressure. Here, we don't shade inside, but the centroid will shade, okay? All right. So now, if I take the diagram carefully, sorry, it looks like broken, but it's actually a straight arrow, okay, because of the animation. All right. So remember, I've taken it now, and we are looking at the side view, okay, this part. So this is what we see. Now, we need to know the value of what? the distance measured from what? The free surface. Here, because the concrete is not yet solid, we assume it to be a fluid with what? A specific weight of that. So we need to measure the height from the surface to the centroid. That's h bar, right? You remember that definition? Okay, good. To the centroid. So this part is here to know where to be known. And then for the distance measured from the free surface to the line of action of the resultant force is the HCP. Here we are talking about the vertical distance, okay? So by definition, we are saying that the resultant force FR acting on one side of the concrete form is giving us what? Because remember, it's supposed to be P times area, right? Pressure times area. And because we are focusing on what? The concrete form, we are saying is P bar times area, where our P bar is hydrostatic pressure, which is actually what? Gamma H bar, okay? The gamma H bar. So from the problem, we know that gamma is giving us what? 23 point what? That's specific weight, right? 23.6 kilonewtons per watt cubic meters. And then that is that multiplied by 1,000 to get Newton per cubic meters. All right. Now, this means that, now if I want to know that of H bar is simply half of this, right? So it gives us the value of what? Half times what? 2.44. That's 2.44 divided by 2, and we have this value. So this simply means that if I know my H and then H bar and then the gamma, I can simply find my P bar. So this gives a P bar to be 28,792 watt Pascal, right? Now, we are still yet to find the others. Now, the area here is actually what? Looking at the area, the cross-sectional area here. That's the area on which the force will be acting. So we're looking at the height times what? The width, which is basically what? 2.44 times 1 point that, and we have 2.9768 meters square. So therefore, we are saying that FR is simply P bar times the area, this value. And this gives us what? 85.71 kilonewtons. Are we good? All right then. All right then. So this is the value. Okay. That is it here. Now we move on to problem 8. Problem 8 is the elliptical gate problem, and it's also an interesting one because here the problem is asking us, or it reads like this: an elliptical gate covers the end of a pipe 4 meters in diameter. If the gate is hinged at the top, what normal force F? This one is hinged here, right? This is the gate, and this is the pipe. The pipe is not cut straight, it's truncated in an angular way, right? By a certain angle. So we are trying to find the normal force that will be required to open the gate, because remember there will be water pushing it down to close it, right? Good. So if that is the case, we are trying to see, hold on one second. All right, so we are to find what normal force is required to open the gate when water is 8 meters deep above, you see, the top of the pipe, and the pipe is open to atmosphere here. Okay, on the other side. Neglect the weight of the gate and take specific weight of water to be this. Okay, so our focus now is on the gate. Okay, good. So let's see here. We have the gate here, but don't worry, I'll extract it later on. So we have it here, and we are to do our analysis on it. Okay, now we know the dimensions or the information provided here will be very useful, so you take note of that. Now, next one is to take the gate. We extract the gate out of it. Now, remember the gate is already, there's a force indicated on the gate acting upwards, right? That's the force we have to find. But remember, in our analysis, all what we've been doing, we don't have the direct formula to compute for this. We have the formula to compute for what the resultant force exerted by what the water on the gate FR. Okay, so that is what we are going to use. This is more or less like an application question. Okay, so we use that idea to help us estimate this force. Okay, all right. So we need to locate the centroid of this gate, and it's somewhere in the middle, right? Remember, it's shaded, right? Part of it shaded. And we need to know the center of pressure of the resultant force, FR. Good. So this one is what we know the formula. We know the formula for the computation of this force, FR. Okay? All right. So now that we've established this, meaning that we can easily play with this. Okay? This is just to show you how to analyze it. But the real deal comes here. Here on the main diagram, we can indicate the centroid here, okay? And we can indicate the distance also here, the FR and then that. Are we there? Good, good. Now, remember that it is hinged at where? O, right? It is hinged here at O. So we have to make some references. Now, if we measure the distance, the vertical distance from the free surface to the centroid of the figure, who can tell me that value? This one. What is this? Yeah. Okay, it's H bar. Okay, H bar. That's the distance measured from the free liquid surface, or here water surface, to the centroid of the gate. Okay, now remember the other one is measured from where? The center of pressure to the free surface, and this is what? HCP. Okay, but remember in all our analysis we'll be using YCP, Y bar, YCP, Y bar, and those ones are slanted, right? But we'll see how, and we did that, how we learned how to play with those ones, right? Yeah, so we'll see. Don't worry. So this one is HCP, okay? Now, we need to know the distance between the centroid and then the center of pressure. And if you remember very well, this is more or less a revision. I'm just giving you the revision here. It's actually what you see is along the slanted height. It's not a vertical height, right? Slanted. So the slanted height is what we are using here. And this is what? YCP minus what? Y bar. Okay. YCP minus what? Y bar. So if I decide to now consider the free body diagram of the gate, I know all this information, okay, off head. Oh, good. So let's take the diagram here. Now, if I take this diagram here, I know this is the free body diagram. So when you are starting to work, you just draw this diagram more or less to give what? The free body diagram. And from here, we know by definition, the formula to find the resultant force acting on the elliptical gate. You know why we are saying elliptical. Remember the pipe is circular, right? But because it's truncated at an angle, the geometry, you know what you learned in development. Yeah, don't worry, you get there. In development, the shape you obtain, you get an elliptical shape. I'll show you later, okay? Good. So by definition, it's giving us what? FR equals P bar A. And this is the same formula we'll be using, okay? But different applications. You see how we use it for the concrete form? Now we are using for elliptical gate. We'll use it for other stuff too, okay? Good. Good. All right. So now we need to find P bar, right? P bar is what? Gamma H bar. And but from the problem, our our gamma is what? This one, right? 9,810 newtons per what? Cubic meters. And then the H bar is simply, look at the H bar. The H bar is measured from the free surface, but from the free surface here to the pipe top, the top part of the pipe is 8. Now from here to here, remember the pipe diameter is 4. So we are looking at the vertical. So it's just half of that, 4. So we are saying 8 plus what? 4 on 2, which is actually equal to what? 10 meters. Are we there? Good. So meaning we have a value for the H bar. This gives what? The P bar to be equal to what? The gamma times the H bar to be that 98,100 what? Pascal. Are we okay? Yeah, I'm rushing, right? Don't worry. You replay the video over and over again and you'll be fine. Okay. All right. So we are moving on. So upon simplification, we have what? 98.10 kilo Pascal. Are we good? Good. We need to now obtain the FR. So for the elliptical gate, we need to know what the elliptical gate looks like before even obtaining the formula for it. Okay? Now, the elliptical gate, look at the free body diagram. It's like that. You see, the shape here has been provided due to the truncation. So this is more or less like the true shape. If you do development, in some portions, they teach you the true shape. I don't know, even in JHS, some of you did that. Some of you did that. So you can do that. That's a true shape here. So this is why you see on top of what? The truncated pipe. So this shape is what you are going to find the area. You are wondering the formula. Don't worry, I'll tell you. And the formula notes are there. So we are saying that that is the same image here. Now, from the textbook, we have a page where we have the images, and I've been showing this to you. Last time we tackled this problem, I showed you. Now, for the elliptical gate, you need to know these dimensions, A and then B. From the center to the shorter part of the circumference is the B, and then the longer part is what? The A. So the formula is actually what? For finding the area is what? Pi AB, okay? So if you are able to identify the A part of this diagram and then the B part, you are good to go. You know, so good. So now, so by definition, the area is given by this formula. Okay. Now, if you look at the longer part, that means we are talking about this. So from the center to this part, the whole length here is what? Remember, 5 meters. So half of that longer part is what? 2.5. So we've been able to estimate the A. So we are saying that A is what? 5 on 2.5. And the B is actually what? Remember, from here to here is actually the pipe radius, okay? Which is giving us what? What? Yeah, the diameter of the pipe is giving us what? 4 meters, right? So the radius will be what? 4 on 2. So that B gives what? 2 meters. You've really forgotten, eh? Just smile and continue, okay? You'll be fine. All right. So from there, we can compute the area as follows. So pi, we know the value for pi. So we end up having 15.707 meters square. Therefore, now my force FR can be computed as follows to obtain 1,540,856.7 newtons. So approximately, we are talking about what? 1.54 mega newtons. Okay? Good. Now, we need to find F. That is the goal here, is not to find any other value. We are to find the force required to open the gate. Remember, it's hinged here, right? So now that we know this, we know that what comes to mind? How do you find this? Yeah, I asked this question earlier. Yeah, moment. That's right. That's the moment. So we are going to use the moment here. Now we take the moment about the hinge. Always take note of that, the hinge, okay? Don't take it about any point. Take it about the hinge. So here, if we are talking about the hinge, we are talking about O here, okay? Now, we have the force here. The perpendicular distance for F is what? 5. We have FR. The perpendicular distance is yet to be determined. We don't know that, so we can't find that. But we know from here, the centroid to the O, we know the value to go at 2.5. This small part here is what we don't know. That's YCP minus Y bar. So if we know that, we can easily find what? The moment, or we take the moment and we obtain that. So let's first of all obtain a general formulation for the F, okay? So to find F, we are saying that we take moment about point O such that clockwise moment, okay, about point O is 0, such that the anti-clockwise moment are positive, right? Okay, good. So that's F times 5. Look at something here. This is the hinge, right? So if I decide to pull F, it's turn it about clockwise. So here is positive what? F times the 5. So that is why we have positive value. You know, so now the other force to consider is FR. Is it minus or positive? Anti-clockwise. So it will turn it about this way, anti-clockwise. So minus FR. Now let's look at the moment arm. FR times, look at something here. Is this distance YCP minus Y bar plus 2.5? Okay, that's why I have these brackets here. And then we equate to what? 0. So from here, if I make my, if I consider a diagram again, I'm just making some clarifications, okay? The YCP is actually here. Okay, this is what I'm calling the YCP minus Y bar. Okay, so from here, if I make my F the subject, I have F, the whole of this across the equal sign, divided by 5. So the only thing I need to know is to determine what? The YCP, Y bar, because I already know FR and everything here. But we have to recall that YCP minus Y bar is actually equal to what? I bar all over what? Y bar times A. Fluid maker, you say a lot of formula. Don't worry. If you know these things, they are not difficult, okay? All right. So we have these things here. We have these things here, and you'll be fine, okay? So we just need to find I bar. Now, remember from the diagram I showed you earlier, I bar is the second moment of what? Area, right? The moment of inertia about the centroid, right? XX. So here is giving us what? Pi A cube times B all over 4. And we've established A, small a already, small b already. So it's just a substitution. Okay, good. Okay, all right. So let's see here. We are continuing, okay? So we are going to use the formula YCP minus Y bar and that. And then we'll see what we can do about it, okay? All right. So now that we have this, we move on. I bar is pi A cube over that, A cube B over 4. And we've established these things already. So A is 2.5, blah, blah, blah. And at the end of the day, we get what? Moment of inertia to be what? 24.5436 meters raised to the power 4. So with this value, we now have to look at what? The Y bar. How do you compute for Y bar? Y bar, we know H bar, so that one is not a big deal at all. So let's see here. For Y bar, let's see the diagram below. Now remember, Y bar is the slanted what? Slanted distance, right? Slanted distance. Because if I know the angle, remember, Y bar, this is H, right? Okay, measure from that. So my Y bar, if I assume it to be the slanted height, and I know my H bar is here. Remember H bar and then the Y bar. H bar is actually Y bar resolved on the vertical, right? Good. So here, the only slanted part here is the gate. So the angle alpha I'm talking about here is actually the angle here. You know so, right? Good. So let's see here. Now, meaning that if I use SOHCAHTOA, the trig ratio, sine alpha is equal to what? The opposite over hypotenuse. So H bar over what? Y bar. You know so? Good. And also, remember that here, I'm looking at what? The alpha, okay? Is here. if I look at this alpha here, it means that sine alpha here is actually equal to what? Sine alpha. Sorry, let me put this line here to cover this. Sine alpha is actually this angle here. Okay, this angle here. This is what I'm talking about, this angle, okay? So sine alpha, remember, this is from this diagram. Because anytime we have HCP, so HCP, the Y counterpart will be YCP, and the angle there will be the slanted angle, okay? All right, now from this diagram, sine alpha is simply what? Opposite over hypotenuse. So it's just simply 4, okay? 4 over what? The hypotenuse. So that's 4 on 5. And this means that, or this implies that my sine alpha is actually equal to what? H bar. So I equate these two. And what do I need? I need H bar. I don't need to calculate for what? The alpha, because it will be long things, okay? I just have to calculate for what? The Y bar. So from here, my Y bar can be computed easily as this. So you neglect this one and consider just these two that I'm talking about. The H over Y, this expression. So with that, we can obtain what? This expression. And then we end up having 12.15 meters. So now that we have this, and remember our equation, so upon substitution, my YCP from this equation, sorry, where is it? From this equation. Remember, I need a YCP, Y bar here in a way to find the YCP minus that. Okay. So when I do that, I'll get what? My YCP minus that to be what? 0.125, right? So with this equation or with this value, I will now be able to substitute into my force equation that we derived earlier. Remember the YCP minus the Y bar was here. Sorry. So with that, we end up having this. Remember, why am I putting times 10 to the power 6 here? Remember, it's 1.54 mega Newton, so times 10 to the power 6, okay? So with that, we end up having the F value to be what? F to be equal to 808.5 kilonewtons. So this is the force required to open the gate. So if it's, let's say you are designing a system, let's say a hydraulic system to lift this, you need a minimum of what? 808.5 kilonewton force to lift that, okay? So this is more or less like, after design this, you now advise management. Oh, to do this part, yeah, you can do this. You put it at this angle. Now, with this angle, any system, you need a power or let's say a force of this to open it. So however, your engineers can come up with a system to produce that force to open. It's up to the management, right? Yeah. Thank you. This is the end of problem 8. And then problem 9 is similar to problem 8. It's quite simple, actually. It's quite simple, actually. Now, it's similar. Now we have to find the force on the gate. The force of the gate on the block as shown. Sorry, you see the block? The block is that small thing here. So we are looking at the force on that block. They've given us where D is what? The distance measured from the free surface to the centroid. Here, the pivot is actually the centroid of the gate, right? Good. Now, look at where the pivot is. All right. So we have this as what? Okay, D to be that. H is equal to 6 meters, and then W to be that. H is what? Here we are saying the gate is of this dimension. Height, this is the H. And then W is the width into the screen, okay? Into the screen, we'll see. That is the W. So if you want the area, you just multiply that by that to get the H, okay? So here we look at how the forces will be displayed, okay? The free body diagram. I'll explain these things. These things will show up later, okay? Now, if you look at this diagram carefully, okay? I have what? the force, I'm taking the gate now. I need to focus on the gate. It's here, right? So I'll take the gate out there. Okay, with the gate here, remember I have the gate in focus. Okay, now the centroid, see, it coincides with what? The center here. That's why it's not showing. Okay, it will cover that. Okay, now I need to know the center of pressure where the force will be acting. This is the force FR acting on the center, right? Now, remember that the force of the gate on the block will be directed this way, right? Right? Good. Now, but the block itself will exert an equivalent amount of force on the gate. So if we're able to determine that, this is what I mean. So the force by the block will be acting this way. So basically, this is the free body diagram. Okay. Now, if you look at this part here, I've indicated FR here. The value here is actually acting on the, what do you call it, the center of pressure. Okay. I didn't estimate that one earlier. All right. So I just focus on it. So by definition, that we have to find F block, but we don't know how to find that. We need to know, we've been told how to find FR. So this is basically an application question too, right? So by definition, the resultant force FR acting on the square gate is giving us what? P bar A. It's the same thing, right? So now where P bar is gamma H bar, now from the problem, gamma is giving us that because it's water, right? Now, we need to know H bar. H bar is the distance measured from what? The free surface to the centroid, okay? And this is the same thing as the D, right? So H bar is the D, okay? Which is what? 12 meters. It was given to us, right? All right. So this implies that my P bar is simply multiplying what? These two. And then I have 117,720 Pascal. So in kilopascal is simply 117.72 kilopascal. So we need to know for the gate now. We need the area because we know P bar. We know P bar now. So I need to know area to find FR, right? Yeah, you are wondering how to get FB, right? F block. You use what? Moment. Yeah, good. Moment. Use moment. Okay. All right. So with that, I have F bar. Sorry. I now consider the area of the gate, and it's a rectangular gate because for the rectangular gate, we are saying it's a square. Yes. I'm just saying that for a rectangle, it's length times breadth, right? But here, because they are all the same, it's a square, right? And that is if you look at it this way, this is what you see. So it's the same thing here. Okay. The same thing here. Now, for a rectangle, what is the area? BH, right? BH. Okay. So H times what? W. Length times what? Breadth. Okay. So we have 6 times 6, and we have 36. So this implies that my FR is simply what? 117,000 blah 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 times 36, and this is what? 4,200,000 and what? 37,920 what? Newtons. So this is actually the resultant force exerted on the gate by what? The water. So how much force will be exerted on the block? So you need to make sure that because this is hinged, if we are not careful, the water will push this thing open, right? Because the pressure at the base here will be higher than the pressure here. So it will be exerted down here more. So good. So if you are an engineer, you put the block here to choke it, where do you go back time? Because here, the pressure here is less, so it will just flip it and then the water will pass through. But if you are designing, you put the lock here, the block here, wabe, rough, you are damn good, okay? Hey, sorry, you are good. So you just work on that, okay? All right. So please, with this, in meganewtons, we have 4.24 meganewtons, okay? So now we need to find the F block, right? To find that, we take moment about point O, which is the hinge, right? And where is what? Our O. Our O is the pivot, right? Right? Good. And also notice that we still need to know the distance here between this, which is actually what? YCP minus what? Y bar. Okay. All right. So the O here, please, is actually what? The centroid here. Okay. That's what I indicated here. So that's, remember, if you look at this, for the block, I know, because the block, the whole of this, we are saying is H on 2, meaning the whole of this height is H, which is what, 6, right? So for the force on the block, or by the block, the moment arm is what? Half of what? H. So from here to here. You know, so we are taking the moment about O. So that one is simply F block times what? And what is that? Is it clockwise or anti-clockwise? We are saying clockwise moment is what? Positive. So about this hinge, this force will turn it clockwise. So positive. F times F block times 3. Okay. Half of what? The H. Good. Now minus FR, we are also taking the moment about this point, not here. So it's simply YCP, this just the small distance here. YCP minus Y bar. So it's just times that. And this one we equate to what? 0. Okay. So all we need to know now is how to find what? YCP. So if I'm able to find YCP minus what? Y bar, I'm good to go. So making F block the subject, I have this formulation. Okay. Now let's move on to the other part. Recalling that YCP minus Y bar is equal to this formulation. And remember, with the rectangular face, we have it this way. And remember, it's a square, so B and H, they are the same. So I bar is simply what? BH cube all over 12, right? So, but for a square or a rectangle, a rectangular gate, I bar is this. So this implies that. Now, look at something here. B, look at the distance here. B is the width, and then H is that. So it's actually the same size, right? So we have 6 times 6 raised to the power 3 all over 12. So this one will give us 108 meters 4 raised to the power 4. Okay, good. So we need to now find Y bar. But remember here, we have everything in H. It is vertical, but we need a slanted what? Distance. Okay. And remember that sine alpha is what? Good. Sorry. H bar over Y bar. So since for a vertically immersed gate, alpha is 90. So meaning what? H bar is what? Y bar, right? So it means that sine 90 is 1. So meaning H bar equals Y bar, right? So which is 12 meters. You know, so this is very, very simple. So upon substitution, we can obtain YCP minus Y bar to be that. We know the area already as 36 meters squared. So this will end up giving us 0.25 meters, right? Good. So this implies that now I can find my force by the block, right? On the gate. So this part will now be simplified to give us 353.33 kilonewtons. This brings us to the end of what? The 9th problem. And then the last problem is the circular gate, the curved gate, the curved gate, the curved gate, the curved. So with the curved gate, it's quite simple, very, very simple, okay? Not that, okay, but I will get there, don't worry. It's interesting, let me put it that way. So here, they are saying that surface AB is a circular, so surface AB, where is my laser pointer? Oh, where are you, Jack? AB is what? A circular arc with radius 2 meters, right? And a width of 1 meter into the paper, or sorry, into the sphere, into the screen, okay? Now, the distance EB is what? EB, where is EB? EB is 4 meters. Now, the fluid above the surface AB here is water. So everything here is water. And atmospheric pressure prevails on the free surface here of the water and on the bottom side of what? AB, this part. Find the magnitude and line of action of the hydrostatic force acting on the gate. Here is interesting on the gate AB. Let's see here. I'll take this diagram again, okay? Now let's take this entire gate here, okay? We need to focus on the curved gate, that's the AB. So I take it here for us to see. Now, labeling AB, okay? Now we know that FR will be acting at what? The center of pressure here, okay? Now, we need to, the resultant force here, okay? The resultant force here is actually, we are looking at what? The water that can be held by this gate, okay? The weight of the fluid that can be held by this gate. Now, let's look at this gate, the fluid here. So this gate is supporting this, right? And remember, there will be fluid here and then that. So if you look at this diagram carefully, there's fluid here and that here. So this fluid here will exert a pressure on this part of the wall, which is this, right? And then the top here, fluid will exert this on this part. So I'm talking about this part of the fluid, okay? So if we're able to talk about the weight here, we'll be able to use that to estimate what? The force FR, okay? Now, look at this here. The A here leaves an image A prime and B prime here. Remember C is here, right? Good. So meaning that the weight exerted or the resultant force acting on this here, the gate, is the same thing as what? The force acting on that. You know, so if we're able to determine FR, that means we're able to solve the problem. Okay? Okay, good. Now, how do we then calculate FR? Looking at this is going to be a little bit complicated. So because of that, we try to focus on the fact that the fluid here will exert a horizontal force here, and then the fluid here will exert a vertical force here. And remember, we've done vertically immersed surfaces and then horizontally immersed what? Gate, right? We've done all those things. So we are going to use them we are applying them here to solve for this, okay? All right. So the next one is to, first of all, look at the forces. So on gate A prime C, I have what? Force AC. And it will act at where? The center of what? Pressure. Remember, the center will be somewhere here, okay? Will be somewhere located here. Now, on CB prime, I'll have what? FBC, okay? Acting. Here is a horizontal plane, so it's acting on the center, okay? Good, good, good. Now, there's also the weight itself. Remember, this force FBC is due to what? The fluid here, right? The top part. And then FAC is due to what? The fluid here. That's what we have in it. What about this what? Sector of fluid. The weight is what we are looking at as W here. So we are accounting for all the forces that will result in what? The FR. Okay? So summing all these forces, summing forces in the horizontal direction from the free body diagram, we end up having what? Fx. So the Fx simply, we have only one force, FAC, right? The horizontal force, we have only one. No, so good. So I have only Fx to be equal to what? FAC. It's just one. Now, similarly, if we sum the vertical forces here, remember they are all acting downward. So I'll have Fy to be equal to what? FBC plus what? W. So if I know this, remember, basic mechanics, I now have horizontal and then what? Vertical forces. How do I find the resultant? The resultant, FR, will simply be what? If you apply Pythagoras, right? I'll end up having FR to be equal to what? Fx squared plus what? Fy squared. And remember, FAC or FAC is computed in the same way as we did for the vertical calculation. Just a question before this one, problem 9. And then the others is the same way we are going to compute for them, okay? All right. So it's as simple as that. Now, by definition, we are saying that FAC, remember, in the normal case, it's actually FR, right? But here, because the curved gate, FR is on the curved part, right? So FAC is simply what? PAC bar AC. It's actually P bar A, right? Good. When our focus on what is what? On the AC. So now remember the centroid is somewhere here, right? Good. And then the center of pressure is here. So my FAC, the AC itself, this is actually the way it looks like, the area. Because we are talking about the volume here, okay? Are we there? So this is the gate. It's more or less an imaginary what? Gate. Okay? All right. So we are saying that width of the gate is 1 meter into the paper. So we've drawn the 1 meter into the paper. You know, so this implies that my area, okay, the area is simply what? 2. From here, what is this? Where from the 2? The height here, how do we know it's 2? We know it's 2 because it's more or less like a radius, right? From here. What they gave here to be 2 meters. So measure from C to B is 2 meters. So drawing a radius, with a radius of 2, we still have the AC to be what? 2 meters. Okay, sorry, the height. Okay, so the area is what? Height times what? The breadth, or the length times the breadth. And remember, the breadth is into the paper, into the screen, okay? So we have 2 by what? 1 meter. So we have 2 meters squared. Now, also with the PAC, we have what? H bar AC. So how do I get my H bar? I measured H bar from what? The free surface to what? The centroid of what? The gate. So now let's see that. Let's first of all identify the centroid here of the vertical gate. The centroid is somewhere here, right? This one. So from the free surface, it's measured from where? This part to that. H bar AC. This is a typical application question, right? Good. So how do I find that? Remember where my gamma is actually, I know my gamma is water, so they gave it to me as this, right? Now, if they don't, assume this, okay? All right. Now I have H bar AC to be what? The distance from here to here. Let's measure from here to here. So I'll add from here to here, which is what? 4, okay? Plus from here to the middle, which is what? Half of 2, which is 1. So I end up having HAC bar to be what? 5 meters, okay? So this implies that I can easily find what? My force AC, my PAC to be that. Gamma is that, okay? Now that I have my PAC, I can find what? My FAC, which is simply what? 49,050 Pascal times what? 2, which is 98,000 what? 100 newtons, okay? So with that, I can find what? I'm saying this is exactly what? The same as what? The Fx. So the Fx component has been obtained. What I'm left with is now the Fy component. So with the Fy component, by definition again, remember this time around, we are looking for FBC. So FBC is actually what? PBC bar times ABC, right? And remember, this one is the horizontal. CB is horizontal. This is it. Okay, sorry. So the centroid is somewhere here in the middle. Okay, so if I want the area, so remember the area will be into the board as that. Okay, so this is the area we are talking about, the surface. So it's actually into the screen. This is what we see. So if you look at it this way, you only see a line, but into the board, you see this. So over here, I know the width into the gate is what? Of the gate is 1 meter into the paper or whatever. Right? Yeah. So over there, the area would then be computed as what? ABC to be the same thing as what? 2 meters squared. Okay, all right. So with this, I'm just animating the area, the gate. Okay, so forget about this one. Okay. So we are saying that this is that. Okay. So my PBC, sorry, H, I've been able to estimate what my area, right? Good. So I'm left with the pressure, PBC. Now, PBC is actually gamma H, right? H bar. Now, gamma is known. So what we don't know is the H bar. So the H bar is actually computed from where? The free surface to the centroid. And it's actually coinciding with the horizontal gauge. So it's just from here, from the free surface to this point, which is just simply 4 meters, right? This is what I mean. This distance, H bar, that. So it's actually the force as a result of what? The load here. Okay, good, good. So it's like we are talking about the pressure here. So length, gamma H bar. Are we good? Good, good, good. So now that we've established HBC, so we can simplify what? My PBC to be that. So that is it. All right. Now, therefore, my FVC is simply what? 39,000, which is the pressure times the area that we compute as 2, we get 78,480 newtons. Okay. Now, what we don't know is the weight. Because we are saying that Fy is actually what? FVC plus what? The W, meaning that at the end of the day, my Fr is what? The Fx squared plus what? Fy squared, square root of that. You know, so now finding the weight of the water held by the gate, we are saying that we have to consider the volume here. And now by volume, I'm trying to extend into the board now. So into the board, I have this, right? Into the board, I have this. So into the board now, I have this. I need to now know. So this area is extended inside. So to find the area, to find the volume, the area, the weight is actually what? How do we find weight? We can start by using the, what do you call it? Force, weight equals mg, right? Mass times acceleration due to gravity. So that's the technique here. And we can get the mass by bringing in the volume. Density, rho equals what? Density equals mass over volume. So if we know the volume here, we can have an interesting game here, okay? Good. So for the volume, I need to know the area of the gate. The area is a sector, right? It's like 1/4 of, it's a quadrant. So 1/4 of what? A circle, quarter of a circle. So this one is easy. Divide a circular area by 4, right? That's it. So here, remember that the weight of the gate is 1 meter into the paper. So by definition, we are saying that weight is what? Mg, right? Weight is mg. Now, also remember that density is what? Rho is mass over volume. The V slash is the volume, right? Which implies mass equals what? Rho V. So I can bring in the volume. Okay, rho V. Remember, rho V is the mass, and then the G is there already. The volume is what? VABC. ABC. Okay, VABC. So with this, how do I get the volume? If I know the area, I'll multiply by what? The length, base area times height. So here the base area is here times the height into the board, okay, or into the screen to get the volume. So if I know the area, I'll just multiply by the length into the board and get the volume. And then I'll use that, multiply by this again, get what? The volume, okay? So here, rho G is gamma, and the gamma is still water. So specific weight of water times the volume. But we are saying that volume is what? ABC, area ABC times the weight, the volume into the board. So we know that where ABC is what? 1/4 of an area. So pi r squared divided by what? 4. And this one, we know the r to be 2, the radius. So divided by that, this gives the area to be 3.143, right, meters squared. And this implies that my volume is simply what? 3.143 times 1, which is that. Now, so we just go on in that. And now that we know my volume, so simply this implies that my weight can be easily obtained as this. The specific weight of the fluid multiplied by what? The volume. And that has been established as 30,832.83 newtons, okay? So that's my Fy, the summation is simply FBC plus what? W, which is equal to what? That. And therefore, we end up having 109,312.83 newtons. Therefore, my Fr, which by definition is given by this, okay, we'll end up having this. And at the end of the day, we get what? 146.88 kilonewtons. This is the resultant force of exerted by the fluid on the gate. Okay, so now finding the line of action. The line of action is quite simple. First of all, here we have 2. We need to know 2. The line of action CP for the horizontal force, because for the horizontal force is FAC, I need to know HCP, right? HCP or YCP. And here is vertical, so it's the same thing. So I'll have what? YCP for vertical, the angle is 90, so HCP will be what? YCP, okay? All right. So by definition, we know YCP is equal to what? YCP minus Y bar is actually this, right? So at the end of the day, we end up having YCP to be equal to what? This. So Y bar, we are here to find, and Y bar, remember, is simply what? H bar AC, right? Because it's a vertical one. That's what I stated here, where Y bar is equal to what? H bar, which is actually HAC bar, okay? And then I bar is actually what? This BH what? It's a rectangle. It's a rectangular gate, okay? So B, remember this. Let's see here. B is what? The width, okay? So into the board, the rectangle, that's 1, right? So 1, and then the height is what? The 2 here, 2 cube over 12, that's a rectangle. Because remember, I drew that one for you to see. I don't know whether I can show you here. Oh, time. Yes, good. This particular one. So into the board, you see this is what? The B, and this is the H, okay? All right, so let's move on. Sorry about that, okay? Sorry. Okay, good. So we have this. So we have them established here. And then meaning that Y bar is simply that. So we've established that HAC bar is what? We had it to be 5 before. So 4 plus 1, that's 5. So we end up having YCP to be that, which is actually HCP, okay? All right, so this is it here. Now, we need to know the line of action of the other one, okay? The line of action for the horizontal one now. Sorry, for the vertical one. Here, I didn't teach you, but I wanted to teach you before. It's actually like YCP, but it's actually, this here is XCP. And the XCP is measured, you know, this one is measured vertical, right? The other one is measured horizontally to locate the line of action of what? FBC. So it's just like measuring from here to here. I'll show you, okay? So let's see here. Assuming my Fy is now the resultant, Fy is acting on that part, right? So I need to know. So line of action XCP for the vertical force Fy, we take what? Moment about this, right? Point C. So we need to No. Why we are taking moment about point C? Because we need to establish how this is going to work, right? Now, if we take moment about point C, remember FBC will have what? A moment about point C, and W will have a moment about point C. FBC will just be half of what? The radius, right? This one, I'll show you how to get that. We need to know the centroid of what? The quadrant. And then we can be able to tell that. And then after that, we need to find what the XP of the Y bar. So the moment arm for, Fy is actually what? The XP. So by definition, this is what I'm trying to say. XP is actually what? That moment arm for Fy. Okay, good. So here, let's see the trick here. We are saying that if I take moment about point C, Fy multiplied by its moment XCP, okay, is equal to, remember, all these things will act in the same direction. Okay, so by default, this is an image, it's a resultant. So this part will be equal to that, okay? So now, here, let's see what is happening here. If I pick this, I'm saying that my, okay, FP, so FBC will be multiplying what? The moment arm from C to line of action of BC, FBC is what? Half of 2, the radius, that's 1, right? Plus, now the W will have a moment arm of what? This value. Because for a quadrant, okay, we will show you that this is for the F, the BC, this arm, okay? So that's why we are showing you the arm here. This one is for the one here, okay? Now, for the W, the moment arm for W, I'm saying that we look at this diagram, okay? The diagram, this is like a quadrant, but then it's this one is a semicircle, right? Good. Now, but the centroid will be on the same line, okay? And the centroid here is this, the arm here. So it's actually 4/3 r on pi. So this is the formula that we just used. So the distance here, okay, is what we are using here, okay? Don't worry, let me show you something. Let me draw something here for you to see. Let's assume that I kind of try to complete this semicircle as this. You see, so you realize that the centroid is somewhere here. So this distance here, this distance here is what we are looking at. Okay, where the weight of the figure will act. That's why we are saying W, okay? All right, so let me clear that one and make it clearer. We are almost done with it, okay? Okay. All right. So that is it. Now the focus is on the, on that. And since we have been able to establish that, okay. All right. So now for the W, we are saying the moment this gap here is this, right? And that is what we just assumed here. So that will now be estimated. And at the end of the day, we'll end up having the line of action for that XCP to be this, right? This formula is known. So XCP, we make it a subject, and we know FBC, we know W, we know FY. So at the end of the day, we put in the substitution and we obtain what? This value. Therefore, XCP is actually this. Okay, so in conclusion, this is what we say. The resultant force acts on the curved surface as shown below. This is it. So at the end of the day, this is the curved surface, okay? So you measure XCP from this part, 0.97, okay? Now, the HCP, remember, we have to measure from this free surface, okay, to that point. But if we are focusing on this point here, it is simply the value we obtained, the 5 point whatever, okay, minus 4. So at the end of the day, we are going to get what? 1.06. Are we there? So in terms of sense, angular, we use what? The equation here to obtain the angle. But in terms of, let's say, the line of action, we can do that, okay? So thank you for your time. And all these things, we obtain them from these diagrams, okay? The others. This particular part 2 of the video is longer than the first part, okay? Just spend time on it and go through them. I hope you enjoy them and try your hands on most of them. I will meet you to discuss the nature of the problems, okay? All right, so I think tomorrow 6 a.m. I need to meet a class. The class rep that will contact me first will be the one I'll meet. Please have fun and enjoy your evening. Bye-bye.